Hey, Vsauce, Lily here. No, I wish though. Anyway, we've spent a lot of time in quarantine by now, and like any other teenager with a debit card has done, I've made a lot of impulsive Amazon purchases. Among them was a penny board, which I've been trying to learn how to ride for the past couple of weeks. And while my brain understands the physics behind it, my muscles still haven't really caught up yet. So as I learn how to program my muscles to catch up with my brain, let's go over the physics behind skateboarding. Wait a second, if we're going to do this right, we have to be safe. Gotta protect those brain cells if we want to do physics. There we go, now we're ready. Kinematics deals with the concepts that are necessary to describe motion, which is important to note because it does not necessarily explain why the motion is happening. For normal cruising, the horizontal kinematics behind skateboarding are pretty straightforward. When you give the skateboard an initial impulse, which will be better explained later, the skateboard moves in a straight line. However, it does not move at a constant speed, as there are frictional forces acting upon the skateboard in the direction opposite of motion. This will be better explained later, but for now, we can consider the frictional forces as our main source of acceleration, or, in this case, deceleration, when looking at the 1D kinematics. By taking some very rudimentary measurements with a slow-mo video and some distance markings, we can graph displacement and, well, rather poorly calculate velocity and acceleration. I'm going to be calculating the initial velocity by seeing how much time it takes the skateboard to cover the first half meter. This is technically a way of calculating an average velocity, but is very similar to the way that a photo gate calculates quote-unquote instantaneous velocity. However, my method is less precise than a photo gate because it takes the average over a longer distance. This means that the skateboard has more distance over which to decelerate than it would if the distance between the measurements was closer. As you can see, it took the skateboard 0.2 seconds to cover the first half meter. Plugging into the average velocity equation, we get an initial velocity of 2.5 meters per second. Doing the same average value calculations to find the final velocity, we get a final velocity of 1.7 meters per second. Based upon the values we know, we actually have a choice between all three of the main kinematic equations. We know delta x is 4 meters because that's the actual distance that the skateboard traveled. We know that the time is 2.02 seconds because of the measurements from the stopwatch. We approximated both the initial and final velocity using measurements and the stopwatch. However, in this case, it would be best to calculate acceleration using the equation x equals x naught plus vx naught t plus axt squared because it only includes one instead of two approximations. Both of the other equations involve using both v naught and v final, meaning that the calculations would be less accurate than if we used more exact known values. Since we're trying to find the acceleration, we solve this equation and we get a equals x minus x naught plus vx naught t all over t squared. Plugging our values into the equation, we get an acceleration of negative 0.26 meters per second. Now, the explanation behind why all this happens will be explained later, but this is what we know for now. 2D kinematics are, well, pretty darn similar to 1D kinematics, except you deal with 2 dimensions instead of 1. One of the more easy examples to look at in basic skateboarding is going down a road that isn't completely flat. In this case, I won't be doing the math for the specific instance in order to calculate the exact angle of the ramp because it would be quite difficult with the number of unknowns involved. I can't really figure out my change in height very easily. I'd have to take deceleration from friction into account, which is harder to calculate when you don't know the angle of the ramp, and I would have to go through the same process as I did in 1D kinematics in order to find the total acceleration. On a ramp, most of the kinematic motion relies upon the angle the surface makes with the ground and the acceleration due to gravity. Regardless of positioning, the force of gravity always points downwards. On a flat road, this is directly perpendicular to the direction of motion, so it only contributes to the normal force, and therefore the friction, but does not directly accelerate the object. When you're going down a ramp, however, a component of the direction of motion is in the direction of the gravitational acceleration. This help from the downward component will cause something moving down the ramp to speed up, but the amount that it speeds up is dependent upon the angle that the ramp makes with the flat ground. On a ramp with a greater angle from the ground, a larger component of the object's motion points downwards, meaning that gravity does more in its overall direction of motion. Since the gravitational force is also less perpendicular with the surface, it also contributes less to the normal force, and therefore less to the frictional force. Taking all of the factors not relating to friction into account, the equation for acceleration on a ramp is A parallel equals g sine theta. Mathematically, we know that sine has a local maximum of 1 at pi over 2, or 90 degrees. So we know that as the angle gets closer and closer to being perpendicular to the flat ground, the acceleration approaches g, which is 9.8 meters per second squared on Earth. Obviously, this ramp example is quite simple. I'm clearly not skilled enough to do some of the more intense, crazy tricks that other people do, but when people do some more interesting tricks, it starts to involve projectile motion, another type of 2D kinematics. Stunts such as this one start with an initial velocity up and horizontal, which in this case is to the skater's right. But after the launch, the skater's skateboard system is in free fall. We're going to ignore air resistance for this scenario because it's pretty much negligible. After the initial launch, the only force acting upon the system is the gravitational force pointing downwards. Because there are no forces in the horizontal direction, there is therefore no acceleration and no change in velocity for the horizontal motion, so the object remains at a constant horizontal velocity for the duration of its airtime. The magnitude of the vertical velocity, however, increases because of the acceleration due to gravity. The initial velocity components depend on the angle that the trajectory makes with the horizontal. Since x is adjacent to the angle, v naught x is solved trigonometrically with the equation v naught x equals v naught cosine theta. Since y is opposite to the angle, v naught y is solved trigonometrically with the equation v naught y equals v naught sine theta. There are a lot of tricks that are even more complicated than the last one. Many of them, including this one, involve a third dimension of motion. Many calculations can still be done the same way, but things like dealing with friction in 2 dimensions gets pretty complicated. This unit starts to actually deal with the whys of motion. Kinematics merely describe motion, while forces explain it. The whys of motion are described in simple terms by Newton's 3 laws of motion. The first one is very simple. An object at rest stays at rest, while an object in motion stays in motion at the same velocity at the point of release unless acted upon by another force. This law justifies why I treated the horizontal velocity as constant in the last situation. There were no horizontal forces, so the horizontal velocity at the point of leaving the first platform remains the horizontal velocity throughout the system's fall. Because the velocity remained constant, the horizontal motion of the system was an inertial reference frame, which is a scenario in which Newton's law of inertia is valid and there is no acceleration. However, the system's vertical motion was non-inertial because it had acceleration due to gravity. Non-inertial frames involve forces, which can be looked at using Newton's second law. Newton's second law says that force is equal to the product of mass and acceleration. In some cases, forces are balanced. When forces are balanced, the sum of the forces in a certain dimension cancel out. This means that there is no acceleration in this dimension. However, when forces are unbalanced, the sum of the forces in a certain dimension do not cancel out. One is greater than the other. This means that there is an acceleration in this dimension. In this diagram, the object accelerates downwards. Many different forces affect motion in skateboarding. One of the most major ones is the force of gravity, which is calculated using the mass of the object and Earth's gravitational acceleration, which is 9.8 meters per second squared. In order to find the force of gravity, aka the weight, of the skateboard in newtons, we need to know the mass. I'm basically going to do this in reverse order. I'm taking the weight in pounds, converting it to kilograms on Earth, and then multiplying by 9.8 to find the weight in newtons. The board is 3.8 pounds, which is 1.72 kilograms when the object is on Earth. When multiplied with 9.8, which is the gravitational acceleration on Earth, we get a weight of 16.86 newtons. The force of gravity is especially important in ramp tricks, in which someone starts from a high height and moves to a lower one due to the force of gravity. During ramp tricks, gravitational potential energy is converted to kinetic energy and vice versa, which we'll get into later. Of course, we know that the skateboard doesn't accelerate to the center of the Earth or something. Since there is clearly no visible acceleration when the skateboard is on the ground, there has to be something balancing out the gravitational force. This brings us to Newton's third law, which states that every action, or force, has a reaction that is equal in magnitude and opposite in direction. When the skateboard is just sitting on the ground, the gravity vector points down with the magnitude of the weight, which, in this case, is 16.86 newtons. This means that another force has to point up with a magnitude of 16.86 newtons because the skateboard is at rest vertically, which must mean that the up forces cancel out the down forces. This reaction force is known as the normal force, and it is the force with which the ground pushes the skateboard up. It only occurs when two surfaces are in direct contact. Since the two forces are equal, they are balanced, and there is therefore no acceleration. Another main force involved in skateboard motion is the frictional force, which I mentioned before. The frictional force is calculated using the equation F equals mu times Fn perpendicular. However, there are multiple types of friction. There's kinetic friction, which is involved in things like skidding and sliding, and static friction, which is involved in things like rolling, walking, and sticking. All forms of friction act in the direction opposite to the direction of motion.
Yet another force involved in skateboarding is the applied force. Anytime you push off from the ground from rest, you are giving the board a horizontal acceleration. This means that you are applying a force. Generally, applied forces are solved for explicitly. There isn't really one equation for it, and it's sort of used to fill in the gaps between the forces you know and the net force you know exists. Putting this all together, let's look at a simple cruising example. Since the board does not accelerate vertically, we know that Fg and Fn perpendicular are balanced. When you push the skateboard, there is a momentary horizontal applied force, and the skateboard starts to move. However, since you stop applying the applied force, and the frictional force acts between the wheels and the ground, the object starts to slow down because the forces are unbalanced and the acceleration is in the direction opposite to that of the skateboard's motion. Work has to do with the transfer of energy. I don't use the word use here because the word use implies that energy is being destroyed and no longer exists. According to the law of conservation of energy, energy can neither be created nor destroyed, so any instance of work has to deal with the transfer of energy. In a lot of cases, however, the energy that is removed from a system is no longer mechanical, as it is in a form such as heat or sound, which is difficult to utilize in a mechanical system. Work is said to be positive if the force vector is in the same direction as the direction of the system's motion. For example, this skateboard is already moving to the left, and I apply a force that also goes to the left. This is positive work, and it puts energy into the skateboard system. I convert the chemical energy in my body to kinetic energy for the skateboard. This type of positive work is often done when shuffling along on the board, or when you're continuously pushing and not cruising. Work is said to be negative if the force vector is in the opposite direction of the system's motion. For example, this skateboard is already moving to the left, and I apply a frictional force that goes to the right. This is negative work, and it takes energy from the skateboard system. The kinetic friction between my hand and the board converts the kinetic energy of the skateboard into heat and sound. Negative work is often done in order to slow down, as the rider either scrapes their foot along the ground in order to convert the kinetic energy of the skateboard system to heat and sound, or uses their foot to create an applied force in the direction opposite of the skateboard's motion in order to decrease the kinetic energy of the skateboard system. There are two main categories of forces that we have to look at when we consider work: conservative forces and non-conservative forces. Conservative forces can both add energy into a system and subtract energy from a system. Because of this, they are path independent, which means that the work they do is dependent upon the displacement and not the distance traveled. This includes forces like gravity, which come into play in stunts like the one I showed you earlier. Even though the skater falls in a parabolic way, the same work is done by gravity in his case as it would have done if he dropped straight down from the top or slid down on a bumpy ramp. As long as his change in height remains the same, gravity does the same amount of work on the skateboard system, regardless of the distance traveled. Non-conservative forces can only either add energy into a system or subtract energy from a system. Because of this, they are path dependent, which means that the work they do is dependent upon the distance traveled, not the displacement. Let's say that both of these skaters start off with the same initial velocity, there are no applied forces, and there is friction, which is a non-conservative force, between the skateboards and the ground. The skateboarder on the right would not get as far along the road because the ratio between her distance traveled and her displacement is greater than the ratio of the skateboarder on the left. The skateboarder on the left takes a direct path, which means that the force acts on her for a smaller distance than it does for the other skateboarder, meaning she doesn't lose as much kinetic energy. There are many different types of energy involved in skateboarding, but the most obvious is kinetic energy, or the energy of motion. At any given moment, the kinetic energy of a system is 1/2 mv squared. Energy is the antiderivative of force and can be alternatively calculated by taking the integral of the dot product of a force field vector and the derivative of the position vector.